You ever wonder what the real secret is to writing truly fast, efficient code? Well, today we're pulling back the curtain on how the world's best software gets its incredible speed. And spoiler alert, it isn't magic. It's all about choosing the right data structure. So let's dive in. So here's what we've got on tap for this explainer. First, we're going to uncover that secret behind apps that just feel lightning fast. Then we'll get into how you actually measure performance, super important stuff. After that, we'll open up the programmer's essential toolkit piece by piece. We'll even touch on data that's all connected, and probably the most crucial part, how to choose the right tool for any job. All right, first up, let's get right to the heart of it. The big challenge every single developer runs into: performance. I mean, it's one thing to write code that works, right? But it's a whole other ballgame to write code that's fast. And you're about to see that how you organize your data, well, it's pretty much everything.
I mean, we've all been there, haven't we? You tap a button on an app, and it's instant. Then you do the same thing in another app, and you get the dreaded loading spinner. What is going on there? Is it just, better code? Well, not quite.
So here it is, the big secret. The unsung hero of all high-performance software is the data structure. Seriously, it's the skeleton, the framework that holds all your data. And picking the right one is literally the difference between an app that flies and one that just flops. Okay, so to really get why this matters so much, we've got to learn how to measure performance in the first place. You can think of it like learning to read the tech specs on your tools before you buy them. It's about knowing what you're working with.
And the big idea here is something called time complexity. We measure this with a handy little thing called Big O notation. Now, don't let the name scare you. All it is a standard way to answer one really, really important question. As my data gets bigger, how much slower does my code get?
This right here is basically our performance ladder. At the very top, you've got O1, or constant time. This is the holy grail, folks. It means your code speed doesn't change no matter how much data you throw at it. Just below that, O log n is wicked fast. Then you've got ON, or linear time, which is still really good. It just means performance scales in a straight line with your data. Think of these as efficiency ratings for your code. Okay, to really make this click, check out this comparison. ON performance, that's like I hand you a giant, messy pile of 1,000 papers and say, find the one with my name on it. You might have to check every single one. But O1, that's like I hand you a neatly numbered stack and say, hey, grab me paper number 5. Boom, you go right to it. That is the power of good organization.
All right, so now that we know how to measure the cost, it's time to open up the toolkit. Let's look at the essential data structures that every single programmer should have under their belt.
Now, this is kind of our cheat sheet for what's coming up. We're going to walk through each of these, so don't feel like you have to memorize this all at once. The most important thing to see here is that there is no single best data structure. It's all about trade-offs. You might get super fast speed for one operation, but you'll pay for it somewhere else. Understanding that is the real key.
Okay, let's kick things off with the one you've probably heard of, the array. The best way to think of an array is like a digital filing cabinet. Every slot has a number, an index. So if you need to get the item at position 10 or position 1000, you can just jump straight there. That's that beautiful O of 1 access we were talking about. It's just instant. All right, next in our toolkit is the linked list. Now this one's totally different. Forget the filing cabinet. Think more like a scavenger hunt or a chain of treasure chests. Each little node or chest holds your data, but it also holds a pointer. Basically, a little map to the next chest in the chain. And this design makes it incredibly easy to add or remove links anywhere you want. And this is where we see that trade-off in action. Let's say you need to insert something right in the middle. With an array, oh man, you have to take every single element after that spot and shift it down one by one. That's a slow ON job. But with a linked list, you just kind of rewire 2 pointers. You tell the one before to point to your new item, and your new item to point to the one after. Bam, O of 1, done. See? It's a classic battle, fast access versus fast changes. So, what if you need the best of both worlds? What if you need to find things fast, like an assorted array, but you also need to add and remove things without that horrible shuffling penalty? Well, that's where the balanced tree comes in. It's like the ultimate organizer. It keeps everything sorted for you, and its real magic is that every time you look for something, you cut the remaining search area in half. That's how it gets that amazing O of log n speed for searching, inserting, and deleting. It's a powerhouse. But what if you don't care about order?
and you just need the absolute fastest way to find something. Well, say hello to the hash table. This thing is basically a magic dictionary. You give it a key, say a username, and it uses a special function to instantly calculate exactly where that user's data is stored. On average, it's an O of 1 operation. It is, without a doubt, the king of fast lookups.
Okay, so everything we've seen so far, arrays, lists, trees, they all organize data in a pretty linear or hierarchical way. But what about data that's messy? Where everything is connected to everything else like a giant web?
For that kind of problem, we need a graph. And don't let the name fool you, it's a really simple idea. A graph is just a bunch of dots, which we call nodes, that are connected by lines, which we call edges. That's it. And it turns out this simple idea is the perfect way to model all sorts of real-world networks.
And, you see graphs everywhere once you know what to look for. Your social media network, that's a graph of people and friendships. Google Maps finding you the fastest route, that's it solving a pathfinding problem on a graph of roads. Even figuring out the order to do tasks in a big project, yep, that's a graph too. They are incredibly powerful.
Okay, we've officially filled up our programming toolkit. We've got arrays, lists, trees, hash tables, graphs, the whole shebang. Now for the million-dollar question. How do you pick the right one? Let's break down a simple way to think about it.
It really comes down to asking yourself 4 questions. First, what am I going to be doing the most? Searching, inserting, deleting? Be honest about it. Second, what are my trade-offs? Do I need blazing speed more than I need to save memory? Third, do I need it to be fast every single time, or is being fast most of the time good enough? And finally, a golden rule. Always pick the simplest thing that actually works for your needs. Don't overcomplicate it.
So let's try it out with a real-world problem. Imagine you're building a system for a university. You have a massive list of every student's ID, and a core feature of your app is to check like thousands of times a minute if a given ID is valid, if it's on the list.
So let's use our guide. What's our most frequent operation? It's searching, right? We're checking for an ID over and over. We need that to be as fast as humanly possible. So, the smart choice? It's the hash table, no question. That beautiful average O of 1 lookup time is practically built for this exact scenario. It makes those checks feel totally instant.
And really, that brings us to the single most important thing I want you to take away from all this. The biggest jumps in performance, they don't usually come from some super clever, tricky algorithm. They come from making a smart, simple choice about the right data structure at the very beginning. It is one of the most powerful optimizations you will ever make in your entire career.
So there you have it. You now have the fundamentals. You get the trade-offs. You know when to reach for an array versus a linked list or a tree versus a hash table. You've got the essential programmer's toolkit. So the only real question left is, what amazing problem are you going to go solve with it?